Hello, my name is Joe Evans. I am from Radiant Technologies. Welcome to the first video in a series where we will explore the physics of capacitors, explain how Radiant's testers measure those capacitors, show what the results should be, and define what those results mean. The purpose of the videos is to help you more effectively use your Radiant test equipment and properly interpret your results. Why use this type of measurement instead of the traditional measurement for capacitance performed by capacitance meters, impedance meters, or network analyzers? The reason is that those instruments assume that the capacitance function in the device under test is perfectly linear. A perfectly linear device responds with a perfectly linear line. A perfectly linear line can be described with only two coordinates. And in the case of capacitors, one of those coordinates is 0, 0. Zero charge at 0 volts. Linear capacitors can be defined by a single number, the slope of the line they make on the plot. Nonlinear capacitors, on the other hand, have curvature. They cannot easily be defined mathematically, so we plot them instead. In this first video, we're going to study the function of the simple linear capacitor. We're going to show how the testers measure that function, and we're going to study the limits of measurement. By the end of the video, you should be able to look at a Radiant tester and know what the drive output does and what the return input does. You should be able to execute a hysteresis loop and understand what is happening between the tester and the capacitor being tested. And you should be able to determine the performance envelope of your tester and compare it to the performance of other testers. A theoretically perfect capacitor is formed by any two conductors separated by a non-conductive gap. Even two wires next to each other form a capacitor, albeit a small one. If the conductors are plates and the lineal dimensions of the area of the plates are much larger than the size of the gap, the math gets real simple. Charge equals capacitance times voltage. Or in engineering parlance, Q equals CV. What this equation means is that when a voltage is applied across the gap of a capacitor, electrons move onto the plate connected to the negative side of the voltage, and an equal number are pulled off the positive side. Let's start with definitions. The electric field is a fundamental force in physics, a fundamental force in the universe. It is the attraction or repulsion between groups of charged particles. Only electrons move in our circuits, so the word electron will be substituted for charged particle in the remainder of this video. But in reality, any charged particle creates an electric field. An electric field is applied across the gap of a capacitor by forcing electric charge onto the plates. The resulting voltage across the gap is defined as the gap distance times the electric field. It is the amount of attraction across the gap. Now we have defined the electric field as the force per charged particle, so the voltage really means the force across the gap distance per electron. And as we know, force times distance is defined as energy in physics. So in the end, voltage is defined as the energy given to each electron by the applied voltage. In summary, a capacitor stores electrical energy and gives it back. How many electrons are stored in a capacitor per volt? We define a capacitor's capacity as the number of electrons forced into the capacitor per unit of energy stored in the capacitor. So C equals number of electrons per energy stored. Therefore, the number of electrons stored can be computed by multiplying the number of electrons that can be stored per unit energy times the energy per electron, which is the voltage. Q equals CV, charge equals capacitance times volts. Capacitance is found by measuring the charge at each voltage and dividing that count by the voltage. It's a very simple definition. The definitions we just studied are for two capacitor plates with nothing between them, a vacuum. If we put any material between the plates, air, wood, water, ceramic, the number of electrons per volt increases. The ratio of that increase to the number of electrons with a vacuum is the relative dielectric constant of that material. In summary, all capacitors of any type store electrical energy. For linear capacitors, capacitors with a vacuum or a linear material between the plates, the count of electrons per volt never changes. For nonlinear capacitors, capacitors with a nonlinear material in a gap between the plates, such as lead zirconate titanate ceramic, the count of electrons per volt depends on the circumstances of the test, such as voltage history, temperature, pressure, or even how long the capacitor has sat on the shelf unused. As you can see from the animation, the volts across the capacitor correspond to a specific number of electrons or charge in the capacitor. So how do we measure capacitance? We count the number of electrons that go into or leave the plates at each voltage starting at 0. This requires a voltage generator and an electron counter. The tester packages both the voltage generator and the electron counter in the same enclosure. On radiant systems, the drive delivers the voltage stimulus while the return counts the electrons moving into or out of the other side of the capacitor. It is important that the return holds its side of the capacitor at 0 volts no matter what happens on the drive side. The reason is so the drive voltage always represents the voltage across the capacitor. The circuit holding the return input to ground potential is called a virtual ground. How do we plot the results? The count of electrons goes on the vertical axis, while the voltage at each count goes on the horizontal axis. A perfect linear capacitor is shown in the animation. It forms a straight line on the plot, and it always has 0 charge at 0 volts. A real-world capacitor made with polystyrene between the plates is shown on the left. Its plot is on the right. It is nearly a perfect linear capacitor, so it shows a straight line trace on the plot. A capacitor made with lead zirconate titanate ceramic between the plates, however, yields a completely different plot. Why do we want to plot the capacitors in this way? Linear capacitors can be defined by a single number, the slope of the line they make on the plot. Nonlinear capacitors, on the other hand, have curvature. They cannot easily be defined mathematically, so we plot them instead. Why even measure nonlinear capacitors? Linear capacitors can be defined by a single number and are used in electronics, computers, and electric vehicles. They are easy to understand. Not so nonlinear devices. They respond to the environment and allow us to make all kinds of interesting devices, sensors, and actuators. Memories, infrared cameras, security sensors, ultrasonic systems, fuel injectors, accelerometers, vibration sensors, and in the future, walking, flying, swimming, micro-robots. Imagine that. Now that we've studied the function of a capacitor and how test equipment measures that function, we need to look at the limits of measurement. No measurement is perfectly accurate, so we need to establish what constitutes an acceptable level of accuracy in a measurement, and that in turn determines what the performance envelope of your test equipment is. You would hope that the airliner pilot knows the performance envelope of his or her equipment inside and out when you're sitting in the back. You should know your test equipment the same way. That way, when you present data in a journal or at a conference, you have a reasonable expectation that your data accurately represents your work. Radiant defines its tester ranges by 3 parameters: voltage, frequency, sample area. The sphere formed by these 3 parameters is the envelope within which the associated radiant tester will maintain 0.5% accuracy of any measurement for a single pass with no filtering of the data. Following are descriptions of the performance envelopes of the 4 research-level nonlinear material test systems offered by Radiant: the RT66B, the Precision LC2, the Precision Premier, and the Precision Multiferroic. The RT66B provides inexpensive test capability for research groups just learning to fabricate nonlinear materials. The Precision LC2 offers the full range of test capabilities residing in the Vision library with a performance envelope much larger than the RT66B. The Precision Premier and Precision Multiferroic test systems are the most powerful offered by Radiant. Many of their specifications are the same, but they differ in their maximum test frequency when using internally generated high voltage. For instance, the Precision Premier can execute a 200-volt hysteresis loop at 3 kHz, but the Precision Multiferroic can execute the same test at 30 kHz. Radiant also offers a unique and inexpensive tester for self-education by engineers. Finding or making your own ferroelectric material to use as a learning aid has always been extremely difficult. Radiant designed and now fabricates a series of packaged ferroelectric capacitors combined with a simple tester plus tutorials to create a system for self-education in the measurement and characterization of nonlinear materials. That is the Radiant EDU. I hope you have found this explanation of capacitance and measurement enlightening. In the next video, we're going to attach a simple linear resistor and a simple linear capacitor to a tester and see what they look like. Thank you for watching.